So, yesterday we stopped here. I just introduced you to the cosmological constant. Now, we will take it further and discuss different aspects of that, and in particular trying to understand what the problem is, because I had already given you a code that people do not understand what the real problem is. So, I will try to justify what I meant by that. So, this problem can be thought of in different ways, but before we sort of plunge into it, I want to first talk about how we describe constant parameters which act as signatures of our universe. Now, if you are completely innocent of cosmology, what I am going to say will make immediate sense to you and you will say it is obvious. But in case you have been already spoiled by some cosmology course, then you will have to do some retranslation. Since some of you must have gone through this cosmology courses, let me try to reorient you on that. Normally in cosmology, when you study cosmic evolution, which is a very well developed field, people use variables which are very convenient to measure observationally and constrain observationally. So, the way they proceed in a Friedman universe is to first look at the expansion rate h0, and from h0 you construct something called a critical density, which is 3 h0 square upon 8 pi g. This is the density which you need if the total matter density, this is for those who are not familiar with it, if the matter density or energy density in the universe is bigger than that, it will recollapse. If it is smaller than that, it will expand forever, and at this critical density it will just coast along. This corresponds to this k is equal to 0 case. Then you take any other object which has some amount of energy density. Suppose you take radiation today, then you take radiation omega r today divided by the critical density C. Let me put a 0 here to say that it is the radiation today divided by the critical density, which you define as something called omega r. You use the capital Greek letter omega. Of course, I should put a 0, but people usually do not put that. And this tells you what fraction of the critical density is contributed by radiation. I can do it for dark matter, I can do it for baryons, etc., etc. And most of the time, observationally, you parameterize the universe by saying what is its h0 value and what are the various omegas. If there is a lambda, you can parameterize what is the omega for the lambda, which is very convenient observationally, but these numbers have no fundamental significance. Okay? So, if you have an observer, an astronomer in a galaxy in redshift of 8, in redshift of 80 we do see galaxies, so maybe there are planetary systems and you can have observers there. They will measure the microwave background temperature to be 9 times the value which we are measuring, like roughly like 27 degrees Kelvin, and he will be measuring all these parameters and he will get different values for that. This I sort of emphasize because suppose you have a theory which tells you that omega lambda is what, let us say pi by 4, then that theory is nonsense, because the omega lambda does not have a invariant significance, it is the value today. Okay? The guy who is, if you say that, on the other hand, if you say rho lambda, because it is a constant and you measure it in some units, of course, the astronomer at redshift of 8 may be using different units, but with some communication you can translate it in terms of the wavelength of the first line of the hydrogen spectrum or some such thing, then you both will be talking about the same thing. But in omegas you are widely off. So, if you are taking fundamental considerations and ask what number is small, what number is big, etc., there is not much point in fooling around with h0s and rho z's and omegas. You actually have to come up with a set of constants which are what I would call epoch invariant. They should maintain the same value today as well as at the redshift of 8, and it should characterize the evolution of the universe. This is not very difficult. I mean, of course, if you have one set of such numbers, any function of those numbers will also be another set. So, it is at that time you try to use whatever is convenient. So, using this, let me give you a description of our universe, which is where you have the real cosmic constants coming in. And I have already said that you want a form invariant description of cosmic dynamics valid at all Z. One set which you can use is this. First, there is a energy density rho qg, which typically is the energy density of corresponding to the Planck parameter. So, you know the Planck length, there is a Planck mass. If you take Planck energy and divide by Planck length cubed, you get an energy density in space. And this is where all our considerations break down. This is very close to the Big Bang. We don't know exactly what this is. This is the energy density at which I want to say some pre-geometric phase has evolved into a geometric phase. And it is in a kind of unknown realm. We know that it is definitely less than some 10 to the 19 GeV, because beyond that quantum gravity will be important, but it could be even lower. We have no handle on where it is, because that pre-geometry to geometry phase transition, if it took a long time, a factor 100, factor 1000, it could have come down. We don't have direct observations on it. Second is rho lambda. That is also an absolute constant, because this is a constant built out of fundamental constant. And I have told you that capital lambda is also a fundamental constant in the universe. I have said that right at the beginning. That is the point of view I am going to take. So, this is another pure number in some units. Then you can define a quantity called rho EQ. It is called the rho equality. So, in the current universe, there is matter and radiation. The matter includes baryonic matter and dark matter, and anything which falls as 1 by a cubed. As the universe expands, the number of particles remains the same, so the energy density falls as the number density, and that is going to come as 1 by a cube. And radiation falls as 1 by a to the power 4, because the wavelength also gets shifted. So, if you take the radiation to the power 3 and matter to the power 4, both will scale as 1 over a to the power 12. So, in this ratio will be independent of a, right. So, this rho matter to the power 4 upon rho r to the power 3 is a pure density number like these two, which characterizes our universe. Because I can compute this at any epoch. A guy at redshift of 8 could have computed it, I can compute it today. We both will get the same number once we have normalized our units, ergs per centimeter cube, let us say. So, this is also equal to, so what does it physically mean? What it physically means is that the radiation density is falling as 1 by a to the power 4, matter density is falling as 1 by a cube. So, if I go back in time, today radiation density is subdominant to matter density. If I go back in time, at some stage these two were equal. When these two were equal, this rho EQ corresponds to either one of them, either rho radiation or rho matter. So, that is its physical significance. Since it is also equal to rho radiation, I can write it as sigma T EQ to the power 4. So, sigma is Stephen's constant, but T EQ is again a characteristic number about the universe. So, if I ask the observer at redshift of 8, what is the temperature of the CMB at which the radiation density is equal to matter density, he will come up with the same number which I am going to come up with. So, this is the signature of the universe. You can construct another universe in which you vary these numbers, and this T EQ can be something else. So, this is an important number in the universe. I am emphasizing because even though it is widely used in observational astronomy, it has never been thought of as a signature of the universe. It is considered as a very convenient parameter to use and things like that. Then of course, corresponding to that, there is also a AEQ. The radiation density falls as 1 over a to the 4, this falls as 1 over a cubed. So, if I take a rho r upon a m, there is a particular number AEQ you can come up for the expansion factor. Instead of setting the value of a to unity today, which is what observers like to do because it is very convenient, it is very convenient to analyze data, a fundamental level you would set AEQ to be unity, because that is the point at which if I set it to unity, observer at redshift of 8 is also going to set it to unity, and then you have a completely natural definition of the evolution of the universe. Now, you can write down our evolution equation, which was a dot square upon a square equals 8 pi g over 3 times the various energy densities. Rho lambda does not change with epoch. Rho matter falls as 1 over a cubed, and rho radiation falls as 1 over a to the power 4, but it can be normalized in this form. AEQ upon a the whole cubed, at a is equal to AEQ, these two terms should be equal. That is what rho EQ tells us. This is a pure number, this is a pure number, this can be set to unity. And even if you do not set it to unity, you can measure every a in terms of that. So, I introduce an x which is a upon AEQ. So, left hand side is x dot upon x the whole square, right hand side is rho lambda rho EQ this. This is the way you would like to describe the universe from a fundamental perspective. It is parameterized by just two numbers, two constant numbers, two epoch invariant numbers. These are the numbers which all observers will agree. Yes. Yeah. Otherwise, you will get one more number. Okay. but I'm going to stick to k is equal to 0 all throughout. Yeah. That's correct. Rho lambda is a cosmological constant. It's like G, H cross and C for me. It's a fourth fundamental constant in the universe. This is consistent with every known observation. There is not a single observation which tells you that the cosmological constant is varying with time. Every once in a while somebody will come up with that observation and it usually goes away after a few months. Yes. I can make some comment about it, but
somebody tells you that omega k is -0.005
mm-hmm.
plus -0.005.
Firstly, there is a fine tuning issue, right? Because if you are talking about omega, then I will ask which epoch. Okay, so you need to come up with an invariant characterization of the curvature. The only invariant characterization which you have is LP square, and if you put LP square, the universe will not evolve at all. So there is no natural length scale, any other length scale has to be fine tuned. That is one argument, but you can do something slightly better if you believe in some of the quantum cosmology models. You can ask what is the probability distribution for different curvatures to come about, and there are toy models in which the k is equal to 0 is preferred. Okay. But this is a comment about the initial conditions of the universe, so it has to be answered in a quantum cosmological context, and this is the best I can do. The same will not apply to lambda. We have no handle on lambda. That is the whole problem. Yes, that's right. Yeah. Yes. Mm-hmm. No, I'm going to come to all that. I'm going to discuss all that. I mean, neutrino mass I won't discuss, but I can comment on it end of the talk. But I'm going to spend a lot of time on that. Okay, fine. So this is almost getting to start with this. Now you ask what is the signature of our universe, and you find it's pretty strange. It essentially has three phases and three characteristic energy density scale, and to the extent we know there is no a priori relation with each other from observations or from theory. First you have rho qg. All that we know about it is probably less than 10 to the 19 GeV to the power 4. As I said, the pre-geometric to geometric phase transition, we don't even know how to describe it. We don't know what pre-geometry means. It is just a word. Okay. In that quantum gravitational phase transition could be an extended business. So maybe it will stop around 10 to the 16 or 10 to the 15 GeV because grand unification takes place around that. But between that window, you cannot really say where it stopped. I mean, how long the effects of transient effects of quantum gravity lingers on. So there is some effective density beyond which you need quantum gravitational effect. Second, you take rho eq. This is what you were saying. Its value is something like a few eV to the power 4. And we again don't quite know its value, but we quite know how to fix its value. I will come back to it. I will come back to what it depends on. Then you have a rho lambda, and that again, if you put it in these units, it will come to this. Now, if you guys are not familiar with these units, let me just take a moment. In natural units, what people would like to think of is to define everything in terms of length or energy. So, if you are taking energy density, that will go as something like energy divided by L cube, and energy will be 1 by L. Why is energy 1 by L? Energy is h nu. H nu is hc upon lambda. H and c are 1. So, it is 1 by lambda. Then it is per L cube. So, energy densities will go as 1 over L to the power 4 in natural units, which again corresponds to some energy scale to the power 4. Okay. So, when h cross and c, if you put it back correctly, you will get your actual number, but it is nice to normalize it like this. So, in energy equivalent, this is like 10 to the minus 3 eV, this is like let us say 1 eV, so to speak. Okay. These are the scales which come about, and this is 10 to the 19 GeV. They are widely apart, so to speak. This number, top number, these two, this is observationally measured, this is observationally measured, straight from observations. Because we know what is rho. This you can compute because we know what is the today's matter. That is why there are plus or minuses. Plus or minus just tell you that there are error bars and all that, and most of the time I have been very gratuitous in giving the error bar. Some of the strong-willed cosmologists will say it is narrower than this, but this is roughly where the ballpark we are. Yeah. Rho QG is. So the assumption is that as you go back, there is some stage where quantum gravitational effects become important. Let us say you want the quantum gravitational effects to be important at 10% level. Rho QG is the density at which this happens. Okay? So we know that at rho QG being equal to Planck density, which is this, it definitely is order unity effect. But depending on your point of view and how quantum gravity is going to move over to the classical gravity, it is less than that, but it is of that order, maybe give or not order, it is give or take factors of 1000, let us say. That is what I would say. Yeah. Okay. Now let us again come back to classical gravity sector. There is no H cross, and if you take the Lagrangian or the action, it is every constant has been put in here, C4, G, R and lambda. And I have told you in the very beginning, you cannot form a dimensionless number from G, C and lambda. You can check it out, I mean that is not possible. So there is no point in asking what is the numerical value of lambda, numerical value of G and all that. I mean you can, it doesn't make sense, it depends on the units you use. So in the classical matter-free gravity, there is no fine-tuning problem. Stress that it is matter free, I haven't added a matter Lagrangian here. So when you add matter, something slightly interesting happens. If you add matter, in that original equation I wrote, I had a dot which referred to the cosmic time, dx by dt. Now I have rescaled the time by taking h lambda. I don't want to use h naught because that depends on today. But very conveniently I have a h lambda, because if I take in this equation, instead of this rho c, I put rho lambda, I get a h lambda. That is a universal number because rho lambda is universal. So I rescale it with respect to that. So I get a very nice dimensionless equation, and that rho lambda which was hanging around there has gone, because that rho lambda is used to transform to this star with all the squares and whatnot. So does all our 8 pi g's, etc. This is a very beautiful equation. This is extremely simple. The universe in nice dimensionless form when you describe is described by a single number, not even 2. And that is a dimensionless number which stands for rho lambda upon rho eq, which as we have said can be defined like this, and you know everything about it, so you can compute it. So this is again sum to the power 4. Now you decide whether you want to worry about sigma or whether you want to worry about sigma 4. Now I would say that you should worry about sigma 4 because that is this quantity. Just because you wrote something is 4, I could have said sigma to the power 17 and say that it is a very small number, that is slightly meaningless. So you should look at this number, that is like 10 to the minus 10. So there is a classical cosmological constant problem if you add matter to gravity. Without matter, there is no classical cosmological constant problem. If you are looking in the real universe, this is something which people don't talk about, so it's important, is that there is lambda here, and I am scaling it with respect to the only other density I measure from the matter sector. By matter I mean any non-cosmological constant sector. There is radiation and matter there, and this number is sufficiently small. It is like 10 to the minus 10. So you can ask, why is it 10 to the minus 10? Yeah.
What do you mean by small?
We will come back to that. But anything which is significantly small compared to unity, I call it small. So 10 to the minus 10 in that sense is small.
How do you decide what is significantly smaller than unity?
No, you give me your significance level. You can say that only 10 to the minus 200 is small. In that case, there is no problem. But most people will say that something below something like 10 to the minus 3, etc. are already small. These numbers don't naturally come up in physics. Okay? So that is the point. So the objective statement is that this is 10 to the minus 10. Our universe is constructed with 10 to the minus 10. If I have constructed this with unity, then the cosmological constant would have started dominating the universe when the matter and radiation energies are equal. Okay? Then the kind of structures which we see would not have been there. But this is not the standard lambda LP square being equal to 10 to the minus 120 problem. This is a different problem saying, why is it that there are 3 energy densities, radiation, matter and cosmological constant. 2 of them were equal at some epoch, but this cosmological constant equality came later on. Okay? So, there is this issue, we do not know this, and in fact, we are not even sure whether it is a meaningful question. So, now let us go back. The reason I brought this up is that everybody says, lambda has a fine tuning problem and all that. So, everybody says it is 10 to the minus 122. This brings back to your question. If you compute rho EQ, you get this number. Okay, this is precisely your point that this number everybody says 10 to the minus 122 writes papers, laments about. Nobody worries about this number. Okay. So, your threshold of smallness is somewhere between 113 and 122. There are two questions. Yeah, let me take that. No, I am not defining it in what sense? You are defining it at a particular epoch, meaning? You are saying it is not a fundamental constant. No, but my definitions of fundamental constant is whether a guy at a redshift of 8 astronomer will agree with me. So, if the redshift 8 astronomer has developed a quantized theory of gravity and I have developed a quantized theory of gravity, we both will be able to measure exactly when quantum gravity effects are important at 10% level, and we both will get the same rho QG. So, I am not using an epoch in the sense of saying that today, yesterday at redshift of 3. I am using an epoch by a physical phenomena, and that physical phenomena is same for both these guys. Therefore, it is an invariant parameterization. Yeah. Right. No, I am going to come to that. I know where you are coming from, and I am not going to discuss it at great detail, but I am going to mention a few things. Okay. So, everybody gives bad press for lambda because of this, but they are not going to do this for this. Question is why? And the reason is that it is somewhat related to what you probably were going to say. We do have a framework to compute rho EQ. We roughly know how to do that. We might not have got it right, but we have a framework. We have absolutely no way how to compute this lambda, except I believe I have, but that is last lecture. There is also this feeling that lambda has something to do with LP. Not everybody believes in it, but most people think that there is some kind of a quantum gravitational connection to cosmological constant, because it again comes from the initial conditions for the universe, etc., which may or may not be true. So, this is why, so here is your rho EQ coming up. There is a formula I can write down for the rho EQ. This is all the dark matter which is present, including massive neutrinos, and then the number of dark matter candidate divided by n gamma, and if there are different varieties, you put a sigma I on that. Okay, so all of them. Then you take the baryonic sector and you put NB upon n gamma. Then you rise to the power 4, you can get rho EQ. So, if a fundamental theory tells me, suppose you think of one species of dark matter particle which dominates, then you have, the theory should tell me what is the mass of the dark matter candidate. It should tell me what is the baryon to photon ratio and what is the n dm to n gamma ratio. In principle, we believe this can be done. Right now we have no clue what the dark matter is made of. We also are not very good at predicting NB by n gamma. There are several models which predicts it, but the value is consistent with what we see, but it is not unique. But in principle, so I have said that in practice we do not have a unique prediction, but in principle we know how to compute it. Okay? And if neutrinos are milling around here, its masses and this energy scale we are talking about is pretty close, and it can give you some way of understanding this, etc. So, we believe we can understand that eventually. That is, we have a hope regarding rho EQ. But if you, so this is what I have said, the high energy physics will eventually fix the value of this, but we have no clue why this quantity is some number like this. Okay. So, this number is here in 10 to the something, this is more natural to write in terms of E, and it is e to the minus 283. Does it sort of tally with what you are going to? Yeah, okay, fine. Okay, so this is the problem with guys who know cosmology. Okay, so this is the main point. That is, there are two constants You don't give bad press to one, but you give bad press to other because this is coming in a red band. We don't even know how to approach the problem. It is not so much that you do a calculation and you get it some 3 orders wrong or something. For example, photon to baryon ratio, you get a wide range of values, but we roughly know what are the ingredients which has to go into it, and once we know the high energy physics model, we believe we can compute it, but we don't know this. So now let us go a bit further. This has to do with the value of lambda and the vacuum. Now this comes under the list of vaccinations, so that later on when somebody tells you this, you can put up your hand and say that that is wrong. Even good textbook, there is a huge number of literature which tells you that 0-point energies should give you a rho lambda. Okay? The argument goes something like that. You take half h cross omega k, which is the 0-point energy of a field, and you integrate over d3k. Of course, it is divergent, but we don't know the theory at Planck scale, so you would evaluate it with a cutoff. So at very large k, this is going to go as k, all the mass scales will go away, and this is going to give you some k cubed. So the total thing is k to the power 4. So the maximum k max to the power 4 is what you get, and it corresponds to some L minimum in this kind of behavior. And the claim then is that, oh, there is 0-point energy of the fields, and that should contribute to rho lambda. And this is coming from very early days of quantum field theory, where you can pardon them because people were still understanding things, where people computed this and they said that if this value is anything like what one would have expected, like Planck scale or whatever, universe could not have existed. They knew that. And so there was this question as to how much it should be, and debates like this. This is completely wrong, and I'm going to spend a little bit of time doing it correctly and tell you what you come up with. The reason for this is that this ties up with something which we did long back in the QFT basics in the early lectures, where I did come up with this expression, okay, as the energy density. Then I said that we are dealing with divergent quantities, so take it only as a heuristic thing, don't take it seriously. But if you want to compute it, how do you compute infinite expressions and get finite things out of it? And since I haven't talked about it at all, I thought I will at least illustrate it in this case, where you will also understand what happens when you do it properly. So if you do this properly, I'll first tell you why this is improper. I will do this improperly. I will show you what is the problem with it. And if you do it properly by using something like dimensional regularization, which I will explain to you what it is, you end up getting a result which is like this. Okay. This result was also known pretty early on. People like Zeldovich has contributed to it. What you get is not something like a cutoff scale to the power 4. The cutoff scale sits inside a logarithm, and what you get is the mass of the system. If this is k square plus m square, that mass of the system gives you the scaling m to the power 4 times this quantity. You assume that this is much larger than that, so that you better get the correct sign. That means, for example, photons do not give you cosmological constant. They have 0 mass. Okay? So 0 mass particle just goes out of the window, only the remaining things contribute, and this is what a proper computation gives you. What do I mean by proper? There is a very systematic way of tackling divergences in quantum field theory. At first sight, it will look as though this is completely shady. After you have studied it very well, you will still think it is shady, but it works. Okay? So the it works part is what I am going to emphasize, and that it works part tells you how to compute these quantities, and dimensional regularization is one of the ways of doing that, and I will describe that. Now, if you do that, your lambda effective is a lambda bare plus this quantity in this calculation, but that is just the way people try to do this. So this sum should be equal to what you observe, so you are able to adjust this lambda bare in such a way that whatever masses are around, it should tackle with that, which is again a question of fine tuning, because you don't know why a fundamental constant like lambda has to be adjusted to this, but we don't have an answer to that. What is worse is this point, and this is the real problem about cosmological constant. The point is that as the universe has evolved, we have very good reason to believe from laboratory physics. The laboratory physics meaning good laboratory, that is 100 GeV CERN-like laboratories, where we understand the standard model and electroweak unification, and we have seen the Higgs particle. So if these ideas are correct, then we have used potentials with different kinds of minima. So it went from a false vacuum, so to speak, to a true vacuum at some stage. And the true vacuum, nobody has any reason why it should hit 0. Even if I lifted it up, matter sector will not care. This is the point I made right at the beginning, and that is the only problem with cosmological constant. If you add constants to the matter sector, gravity picks it up. We don't want gravity to pick it up. This breaks the symmetry. That is, adding a constant to a Lagrangian is an invariance, is broken by gravity, it picks it up. This is the problem. And that happens even at, in quantum field theoretic language, it is called tree level. So if you are doing some Feynman diagram or something, if you consider scattering of 2 electrons, let us say, you will draw a Feynman diagram like this. These are 2 electrons and it exchanges a photon. But it will turn out that there are other quantities which are contributing at higher level. For example, you can have a process like this. Heuristically, you can think of it as this photon split into an electron-positron pair and then again became a photon and did this. So this is called a loop, obviously. So this computation would be at loop level, which will have coupling constants coming here, 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 here. It's a 4th order object. While if it was only this, there is only 2 coupling constants, so it's a lower order thing. So tree level is the lowest level, and then you have loop levels, etc. So this contribution which we are talking about is at the real lowest level. You are just shifting an energy density in the Lagrangian, and that affects the cosmological constant. It breaks the symmetry and gravity picks it up, etc. Now let us go a bit further. Yeah. Yeah, this has nothing to do with quantum gravity. That is the whole problem. This is laboratory physics. Okay, that is why the problem is serious. We know from CERN experiments or Higgs boson discoveries that the standard model is vindicated up to some 200 GeV or some scale like that, which is well below quantum gravity effects. So at that level, there is a contribution coming to it, and the universe did cross through that. Okay, and that potential, if it was shifted slightly, and there is no reason why that 0 should be fixed at a value where you get this particular cosmological constant today. So you run into a trouble. Okay. So now let me come back to this question as to why I tell you that this half h cross omega integration giving you a cutoff is a bad way to think about it. So 0 point energies do not contribute to cosmological constant. Whatever else it do, it doesn't contribute to cosmological constant. Now there are 2 ways of doing it. One way is if you have actually studied your canonical quantization correctly in some course, somebody would have said something about normal ordering. Okay. So normal ordering is a well-defined prescription by which you can just wipe out the 0 point contribution. Because your Hamiltonians can be, you can add a constant to the Hamiltonian by adding a suitable constant, which is what normal ordering does in a methodical way. There are no 0 point energies. So if 0 point energy is going to contribute to something, then it is a bit shady because we are removing it at that level. But there is but assume for a minute that you don't believe in normal ordering. For example, normal ordering requires you to know what is your A dagger and what is your A in order to put one to the left of the other. And if you are in a curved space-time and then there are Bogoliubov coefficients, etc., you can sort of quibble about it. But there is a straightforward reason why this is a wrong calculation. In order to do that, you just do the calculation correctly and you will find that it is wrong. So the way it works is the following. So let me run it through because we never did canonical quantization in this class. There is a very beautiful review by Jerome Martin, which I have cited here. He discusses various aspects of cosmological constant. It is well worth reading if you are interested in it. Some of these are taken from there. So you have the field equation. This is the time derivative, this is the spatial derivative, this is some square flat space-time. So when you are doing canonical quantization, you have e to the minus I omega t plus k dot x and e to the I omega t, and there is a creation and annihilation operators which are written down here. Omega k is this, and the Dirac normalization for the creation and annihilation operator is this. So as I said, I am just following his own notation. So if you want to go and read up this article. So what you want to compute is, for example, the 0 point energy density, which will be the energy density of this field. And there is a standard way to write down the energy density. it has a phi dot square, then you have the del phi the whole square, which is what is written here, and then half m square phi square. So, you want to compute its vacuum expectation value. So, if you are going to do this, you want to compute phi dot square expectation value. You can almost look at it and write it down, because you must have there is 1 over 2 pi cubed I can put under this d3k. Then this 1 over square root of 2 omega will give you a 2 omega factor, and this phi dot square will give me an omega square. So, this is what you will get for this term. Then if you do exactly this thing, you are taking spatial derivative. So, instead of omega square, you will get k square. And if you are doing phi square, you are not taking anything, therefore, it will just give you d3k upon this. These are the 3 terms if you take the vacuum expectation value. All of them are beautifully divergent, but we will keep them as it is. Then you go and plug it in. So, you want to compute this 0 point energy, which is d3k times omega k, and you also want to compute the 0 point pressure. So, the pressure is taken as a projector. This is delta mu nu minus u mu u nu. This is just you dot it with u mu u nu t mu nu. This is the projector into the transverse phase, 1/3 of that is the projector. So, you again compute it, and that is going to be this quantity. So, let me see whether I get the numbers right. So, I have a half, this is the answer, but let us see. This is half, there is 1/6 and half. So, take a half out first. So, phi dot square is going to give you an omega square, and this is not going to give you anything but m square. So, you get an omega square minus m square, which is k square. Then this is going to give you a k square, there is only a 1/3 because we have taken a half out. So, I have a k square minus 1/3 k square, that is 2/3 k square. Then I have a half, that makes it 1/3 k square. That is exactly what this is. This is 1/3, and that extra 2 belongs to this 2 omega. Okay? So, you get an answer which is this for the pressure. Now, you can immediately see that something is going wrong. Your equation of state is not right. See, if you want to say something is cosmological constant, P should be equal to minus rho. If it is not that, it is not going to accelerate the universe. If rho plus 3p is a positive quantity, you are sunk. It probably is going to do all kinds of things to the universe, but it is not going to give you the accelerated expansion. So, here I get a rho which seems to be a positive semi-definite quantity, and you get a p which is also like this. Okay. So, now let us bravely go ahead and compute it a little bit further. The way people normally do this is how the Baer constant gets added. Let us do it with a cutoff. So, what you do is that you do the integral, angular integrals are trivial. So, in the other integral you put a cutoff at upper scale at some value lambda. So, you cut it off there, and then you are going to compute this integral. This is doable. Once you have put the cutoff, this is a well defined integral. You can look it up or you can do it yourself, and what you will find is this is actually the exact expression. So, you get this, and we are interested in a limit where the cutoff scale is very large. It should eventually become infinity. Then what you will find is there is an m to the 4 upon 16 pi square, and the first leading order correction is some 1 plus m square upon capital M square. So, the 0th order contribution does seems to go as 4th power of the cutoff mass, which is what you would have naively expected if you do a d3k integral over a square root of k square plus m square. Now, you do exactly the same calculation with pressure. So, pressure, your omega comes in the denominator, and there is a k square which was here, and then d3k will give you another k square. So, it is k4. Again you can do the integral, this is the exact result. Now, you go and compute it, and you will get 1/3 of what you got before. Let us see, this is m4 upon 16 pi square at the leading term. Here the leading term is 1/3 of that quantity. Correction times are different, but the leading term is 1/3. So, P is 1/3 of rho, which is the equation of state for radiation, and that is what a cutoff computation does. So, what happens in textbooks is that they will compute this, tell you it is m4, and therefore is a huge cosmological constant. They should stop and compute the pressure as well. They will find that it is 1/3 of this, therefore the equation of state is wrong. So, to the leading order, the 0 point energy is computed like this is not going to contribute. There is one more problem. Suppose you are computing the energy momentum tensor of a cosmological constant. and or vacuum, you want this quantity to be Lorentz invariant. So, if you are going to compute TAB, in particular consider T upper and lower in some expectation value sense, and if it has to be Lorentz invariant, the only thing you can have is some constants time Kronecker delta AB, because anything else will depend on the trajectory of the observer, because in order to compute the pressure and the energy density, we use the u mu of the fore velocity of the fundamental observer, but that is wrong, that is not generally covariant. This result is not generally covariant. Okay? I mean, it is perfectly fine for radiation, because radiation, if it is an isotropic gas of radiation, etc., you have a S prime, etc., etc., and things will transform properly. But if you have some TAB which is coming from the vacuum, which is completely Lorentz invariant, you cannot get this. This is a well-known problem in quantum field theory. This is just an example. This is because the way we computed it, or rather the technical term is the way we regularized the infinite expression, breaks the Lorentz symmetry. Because we took the 3-dimensional integral k and put a cutoff on it. Okay? That depends on the Lorentz frame. So, this is not a Lorentz invariant regularization. So, if you have to do this regularization problem, this was known for ages. I mean, even when quantum electrodynamics came up, etc., people worried about whether your regularization, everybody knew there is an infinity and it has to be regularized, and if you do it in the wrong way, in a non-Lorentz invariant way, you can get nonsensical results or ambiguous results. Later on, when gauge theories, things like that evolved, people knew very methodical ways of tackling this, and one of them is this dimensional regularization, which I will try to tell you. Okay. So, so before I go to that, there is an interesting observation about it. Suppose you just throw away these terms which go as power laws on M, there is some logarithmic term here. Okay? So, suppose you ignore this and you just pick the logarithmic term, then what you find is that this M4 and M4 cancels. Now, it starts scaling with the small m4, and you get a 32 pi square in the denominator. Now, if you look at the corresponding term in pressure, if you take the logarithmic term and this 3 cancels out, this 2 and 16 gives you 32, and again you have got this m4 and that will cancel with this, and you will actually get this m4 back. So, this I have written down here, that if you just pick up the logarithmic term, one of them has a minus sign, the other has a plus sign, and if you just retain this, then it has the correct equation of state. So, somehow you need to come up with a regularization prescription which kills all the power law divergences and retains the logarithmic divergences, which is what dimensional regularization does. Okay, so this is, of course, I cannot go deep into dimensional regularization, but I will just give you a flavor of that, and you will probably learn more about it in some other class, like maybe gauge theories or QZD or whatever. So, what you first do in dimensional regularization, I mean, all regularization schemes are very methodical, very systematic, and very proper way of cheating. Okay? So, but you have to do it properly. You have to cheat in a Lorentz invariant way. That is what we will do. So, what you do is that instead of working in 4 dimension, you work in D dimension. That is what dimensional regularization means. Then your integrals will have an extra parameter D, and which presumably is a positive semi-definite integer. But what you will do is, after you have computed the calculation, you will say that I am going to analytically continue for all values of that D. Okay? Then, of course, in the end, when you put D is equal to 4, the expression will be divergent. If you have done a honest calculation, it will be divergent. But more often than not, and in fact, almost all the cases, you can nicely separate out what are the divergent terms and what are the finite terms. Then there are formal ways of killing the divergent terms, and the simplest thing is to say that I am going to ignore the divergent terms and extract the finite terms. And this entire process is Lorentz invariant, and this is what you do in dimensional regularization. So, you start with exactly the same kind of an expression. So, there is a 2 pi to the d minus 1 by 2, and there is a d minus 1, bad notation, but d minus 1, I mean I am picking it up from Jerome. Okay, so, this is d minus 1 times k, and then you have the creation and annihilation operators. So, you want to keep the dimensions also correct. So, it is nice to introduce a mass scale. So, you put a mu to the 4 minus d, after all when d is equal to 4 it will not contribute. The idea is that when you do this integral and you have omega, this and then this mu to the minus d will exactly cancel out, so that you will get an expression which is mu to the power 4, and mu to the power 4 will have the correct energy density. So, you introduce a scale just in front and then you want to compute this quantity. This quantity of course is divergent at d is equal to 4, in fact it is divergent even at some d is equal to 3, 2, etc. So, you want to compute this integral. The trick is the following: you first look at this integral. I mean, there are different ways of doing it, this is the simplest way to do that. The trick is, you think of alpha the dimension, think of d alpha k upon 2 pi to the power alpha. To take away this feeling that it is a dimension and it is an integer, etc., I have called it alpha, but of course you do it as though alpha is a integer, so to speak. And then you have 1 upon k square plus m square to the power beta, and you do this integral. At least for some range of alpha and beta, which you can easily fix, this is convergent. Okay. So, this integral can be computed. I leave it to you to play around with. I mean, the easiest way is to write this denominator as an exponential with a parametric integration, and then in the exponential you will have e to the minus some lambda k square plus m square. So, e to the minus lambda k square and any dimension d3 is a Gaussian integral, you can perform that, and then you can do the parametric integration. So, then what you will get is this result. Okay. So, there is a gamma function which involves beta minus alpha by 2, and then there is a gamma of beta, then there is a constant, and you will get 1 upon m square to the beta minus alpha. So, this you can compute. Then you quietly take this beta to be minus half, so that you make it go to the top. Of course, it is divergent, but you do not worry about it. You take beta to be minus half and then alpha to be d minus 1. So, what will happen? Okay, so beta is minus half, so this is minus half minus alpha by 2. It is minus half into alpha plus 1. Alpha plus 1 is d, because remember this alpha comes as a proxy to this. So, alpha plus 1 is d, that will give you this gamma of minus d by 2. Then you can already see that when it is d is equal to 4 is gamma of minus 2, which is divergent. Okay. Then this is going to be gamma of minus half. Here beta minus alpha by 2 again we know is minus d by 2. So, put minus d by 2, 2 will kill this 2 and minus d will take it go up. So, that is m to the power d, and in the computation which we are doing here, there is a mu to the 4 minus d and a 2, everything else I have taken care of. So, when you take care of that, you will find that you get mu to the power 4, assuming there are no typos in the formulas, and you get this 2 from that half omega, and then this is your answer. So, you have computed it presumably in d dimensions. Of course, the integral is badly divergent in various values of d, but you just take it as your answer. And you can do exactly the same calculation for p as well. Of course, in p you have a k square here, this is the denominator, but there is a k square here, but that is easy because you write it as k square plus m square minus m square. So, k square plus m square and a square root here will give you a square root, which we know how to handle. Then m square upon this is exactly this one. So, you do that whole computation. Okay. This d minus 1 comes, this is our 1 by 6 when d is equal to, so 4 it is 3 and 3 into 2 is 6. That comes because you are taking a trace in Kronecker delta, and in d dimension that will give you this. Spatial trace will be d minus 1, and that is what gives you this. So, you do this computation and you get this result. This is very nice. So, if you compare this with this, you have this nice minus sign, everything else matches. Of course, what you have proved is infinity and minus infinity, but if you do not worry too much about it, you get an equation of state which is p is equal to minus rho. What it tells you is that we have used a Lorentz invariant technique for regularizing the cosmological constant, and when you do that you get a Lorentz invariant result, which you would have almost guessed. This is what cosmological constant should give. Now, you want to try to extract the finite part and the infinite part out of it, and this is again a well known technology in dimensional regularization. What you do is to set d is equal to 4 minus epsilon and expand in epsilon, and epsilon goes to 0, we know it will diverge, and you pick out the divergent pieces. So, the way one normally proceeds is that if you put d is equal to 4 minus epsilon, remember there was a minus d by 2, that will give me a minus 2 and a plus epsilon by 2 in gamma function. So, you get it to some meaningful gamma. So, start with this gamma of 1 plus epsilon by 2, that is going to be gamma of epsilon by 2 divided by epsilon by 2, because you subtract 1 out of that. Then you get one more, so that is going to give you this minus 1 plus epsilon by 2, then minus 2 epsilon by 2, or I could have started from here. Okay? So, these are the factors which you want in order to finally get from here to here. Essentially, you are using gamma of z and gamma of z plus 1 or the factorial relation. So, you can get this answer, and we know exactly where the divergences are coming from. This is not going to do anything. Epsilon goes to 0, this is finite, epsilon goes to 0, this is finite, epsilon goes to 0, this is finite, but there is an epsilon by 2 sitting here that is going to blow up. Then you look at other terms. I mean, there are things like 4 pi to the power some d minus 2 by 2 or whatever, and that is going to give you something and an epsilon. What you do is that this part is fine, that gives you this. Then you have something to the power epsilon by 2 when epsilon is small. So, you write this something as exponential log of something. So, you get exponential log of epsilon by 2, and then the epsilon is small, so you get epsilon by 2 times log of 4 pi. Same thing you do for m to the power d, which is 4 minus epsilon, you get a factor and a logarithmic term. So, this is why in dimensional regularization most of the time you keep picking the logarithmic term which will survive, but the other terms will not. So, you put all of them together, then you will find that the energy density is given by this expression. And we are supposed to take epsilon going to 0 limit of this. So, this is very standard in any dimensional regularization calculation. This is the sort of thing which you get. And then there are subtraction scheme. There is something called minimal subtraction, and which is called MS, and there is something else called MS bar, which is you take away some more terms out of it. But these are just words, but you will come across these words if you do some QCD calculation or something. What we are going to do is that you see that this quantity is divergent when epsilon goes to 0. So, compared to that 3 by 2 and minus gamma is the Euler constant that comes from the Taylor expanding your big gamma. So, compared to that these two things are nothing, so you throw them away. And by the same spirit, if you look at the log, there is a log 4 pi, take that out, the rest you need to keep for dimensional reasons. So, that log 4 pi also you can subtract it out. So, this whole divergent term you just drop. You say that I have dropped these divergent terms and the finite part is given by this. Okay. So, this is why I said that this is a very systematic way of cheating, because you do these things properly, maintaining all the symmetries of the theory and all that. And a colleague of mine used to tell me that he works in lattice QCD. So, he says the problem with the dimensional regularization is that you never know what you are throwing away. While if you are looking at some cutoff etc., you sort of know what you are throwing away, but here you do not know, but the method works. And this is the result I originally quoted. And this has been computed in very many different ways. This is not the only way it has been computed by taking this energy expression. People have, for example, worried what would interactions do. So, instead of taking a scalar field, suppose I put a lambda phi 4 interaction. Then you want to calculate the energy density contributed by summing Feynman diagrams etc. You do it properly, and in all the calculations dimensional regularization gives you this value. Depending on if you use the same subtraction scheme, you always get this result. So, there is some robustness to this, which is why people like it and people use it. So, this is roughly what I want to summarize the concrete part of the calculation and discussion of the cosmological constant. So, basically just to emphasize, the problem with the cosmological constant is that at tree level, if you add a constant to a Lagrangian, that symmetry is broken by gravity. This is the only problem. I mean, if you solve this, everything else will go away. Second, the conventional calculation of computing just the energy density but not computing the pressure and saying 0 point energy contributes to cosmological constant is simply incorrect. Because whatever he has done, if he does a little bit more to pressure, he will find that the equation of state is formed. If you try to do this correctly, it depends on your regularization scheme, and if you use a Lorentz invariant regularization scheme, you will get the correct equation of state and the form. and its value in dimensional regularization scales with the mass parameter in the theory, and zero mass fields are not going to contribute to the cosmological constant. Rest of them do, but we do not know what is its effect. But all this gets subsumed when you understand that this is all more complicated quantum field theoretic calculation. Even at the tree level, when you add a constant to a Lagrangian, it is doing something. So that is what I want to concentrate on, and in my mind that is the major problem with the cosmological constant. Along the line, I also have told you that the universe can be described in terms of either two densities, rho eq and rho lambda, at least in the classical phase of the universe, and if you rescale everything with respect to rho lambda and time scales coming out of it, it can be described by a single parameter sigma, which is dimensionless, which for our universe has a value 10 to the minus 10. And that is what brings me back to the question that if you look at lambda times LP to the power 4 kind of a calculation, one of them is some 10 to the minus 113, the other is some 10 to the minus 122. And most people think that their threshold of fine tuning is somewhere in between. Most people do not even do that computation. When I ask cosmologists whether they knew rho eq, this is the number, many people get surprised that it is such a small number, that is like 10 to the minus 130, which is what it is. Okay? Fine. Now let us go further. So now I want to shift the gears and say that I have said there is a problem with the cosmological constant, which is namely that when you add a constant, gravity does not respect that symmetry. So the problem is not with the cosmological constant at all. We haven't understood the problem. The problem has to do with gravity. We are doing gravity completely the wrong way around. And where we went wrong with gravity is that we ignored the most important single fact about gravitational dynamics, namely that we want it to be immune to this shift at the zero level of the energy. So this for me is like a postulate, it is like principle of equivalence. So let me put it in context. If you take the standard approach to general relativity, and if you want to do it in a postulational sense, taking minimum amount of observational input, the first thing you will say is that there is principle of equivalence. That tells you that in freely falling frame there is no gravity, and also from that you can reason out, like that clock thing which we did very early on, that gravity is described by a metric tensor. That is the most natural interpretation of that. Gravity is geometry, it is described by a metric tensor. So this is the kinematics of gravity. Once you have given me the metric tensor and you have assumed general covariance that all observers are equivalent, because the metric tensor's form cannot depend on how much is the observation and how much is the intrinsic geometry. This is a point which is not often emphasized, so let me spend a moment on it. If you are in flat space time and you make a curvilinear coordinate transformation, your metric tensor is no longer going to be 1 minus 1 minus 1 minus 1. But if you are in flat space time, somebody can always bring it back to that. Therefore, he knows if you give me a g mu nu, I know how much of it is due to acceleration, so to speak, in a very generalized sense, it is due to nonlinear coordinate transformation beyond Lorentz transformation, and how much of it is due to intrinsic geometry. What is due to intrinsic geometry is eta mu nu, everything extra is because you are doing something crazy in your coordinate system. But in a curved spacetime, there is no separation like that. That is exactly what principle of equivalence tells you. You can't distinguish acceleration from real gravity. So if I give you a g mu nu, you cannot say g mu nu 1 is due to the intrinsic background curvature and g mu nu 2 is because you chose a crazy coordinate system. It breaks general covariance because any coordinate system is as good as anything else, and it violates principle of equivalence, which tells you that acceleration and gravity together is what you can measure. The old Resnick and Halliday, you are sitting on a weighing machine going up in a lift with some acceleration, Earth's gravity is this much, what will the weighing machine show? So the weighing machine will show the sum of the gravity downwards and the acceleration upwards. So it is not going to distinguish between two. Therefore, you cannot naturally assume that your metric tensor can be differentiated between these two, and the kinematics depends on this metric tensor. That is the good thing. And using that metric tensor, you can work out everything, how gravity affects any physical system, you can work out. There is some little thing about whether the systems are actually going to go and couple to curvature. If it does that, then those things you cannot guess by this. but this is what is called minimal coupling. The minimal coupling of any matter sector to gravity is encoded in principle of equivalence. So, principle of equivalence is a very strong principle which tells you all about the kinematics of gravity. What about dynamics of gravity? What determines how g mu nu is going to change with time? It turns out we do not have a principle. Okay? You can do all kinds of crazy things, and this is why there are several theories of gravity which are milling around. I mean, just it has to be happy, it has to sort of be consistent with all the observational tests as long as it is done. If you have parameters in front of various terms in the Lagrangian and you keep them sufficiently small, all the experimentalists can do is to put bounds on those parameters. But, so, if you do not have a guiding principle, you do not know what kind of gravitational theory you want to come up with. What I propose is that this is the guiding principle which we have missed. We already know from whatever, in some sense you can think of it as observation, that there has been phase transitions in the universe and the 0 level is arbitrary. Therefore, the only way you can think of this is this. There is another way to think about it, because I have said that gravity breaks a symmetry. So, an operational way of talking about this is that if you add a constant to L matter, the matter equations remain invariant, but the gravitational equation does not. Actually, this is a slightly stronger statement can be made, which is important to us. You can actually prove a theorem, it is not much of a theorem, it is fairly straightforward to prove, that if you have gravitational field equation derived from a local extremum principle. By local extremum principle, I mean that there must be some density which is integrated over spatial 4 volume. Okay? So, that if you want to think of it as Lagrangian and d4x, that is fine, or you could have thought of it as some entropy density integrated over a 4 volume or something like that. I mean, whatever, there is some extremum principle. I am not saying what the nature of the extremum principle is. In an extremum principle which is local, and the variation of the metric in that extremum principle is what is supposed to give you the field equations. If the theory is generally covariant and the metric is varied in an unrestricted form in dynamical, as a dynamical variable, then you can prove that the equations of motion will not be invariant under shift of TAV. So, if you want to have a quick way of thinking about this, the moment you have this local Lagrangian based variational principle, the volume factor is square root of minus g times d4x. Therefore, if you add any constant to it, that rho, that constant rho is going to go and couple to root minus g. When you vary it, that rho will appear in your field equation. You cannot get out of it. That is where this word unrestricted is important. I mean, it is not probably important for this class, but if you are talking to some experts, he will hit you with a word called Uni Modular Gravity. So, Uni Modular Gravity is a variant of a gravity, where you say that you are going to vary a metric tensor keeping root minus g fixed. I had always found it to be slightly funny. It is like saying that, you know, I do not want to go from 1 to r square sin theta. So, when you go from Cartesian to polar coordinate, root minus g changes. Okay. So, I do not see strong motivation to keep that, but there are people who want to work in that model. There you can get away with it, because it is root minus g to which your rho couples, and you are not going to vary root minus g. So, if you assume, and as I said, there is no motivation for it. So, if you take unrestricted variation and metric is a dynamical variable and the theory is generally covariant, you cannot make this invariant. So, you have to drop one of them. Well, we do not want to drop general covariance. We presumably do not want to drop locality of an extremum principle. So, you have to conclude that metric is not a dynamical variable. You have to get your equations of motion by varying something else, and we will see what that something else is in the last lecture or so. There is also this issue that suppose you fix your lambda, suppose you have some beautiful principle to fix that lambda, because for example, I am going to talk about a principle which will give me the numerical value of the lambda. But I am sunk in the usual models of gravity, because in usual models of gravity I can add a constant. So, after you have fixed it, if somebody added a constant, then the value, the numerical value I have written down has no meaning. So, determining the value of lambda, so to speak, suppose you want a fundamental theory to tell you why lambda LP square is 10 to the minus 123. You cannot do it in conventional models of gravity if gravity couples to that lambda, because when you shift that lambda, this value is going to change. So, you can ask what is necessary to solve this problem. Now that we have identified the problem, I mean we have solved the first part of the Chesterton's court, what we want to do is you have to first make the field equations invariant under this. In the sense that you have some Lagrangian added to this should give you an invariance here. But we do want a cosmological constant. The equations in red are invariant, but the solution should pick up lambda as an integration constant. So, when you are solving for the universe, you have to fix it just once, you have to fix it just only once. There is a universal lambda which has to be fixed. And because it has to do with the universe and how the universe came into being, why our nature is like this, etc., this is again a question at the pre-geometry level. So, some quantum gravitational considerations has to go in, and in this model lambda is linked to LP square, and some quantum gravitational considerations has to fix its value to some non-zero value to do this, and which requires a new physical principle. I mean, you cannot just say that this is the, of course you can say that it is an initial condition, but it would be nicer if you can come up with a physical principle to fix its tiny value. But as I have said, this one cannot be done in generally covariant theory if you are going to vary metric to get field equation. So, you need a new variational principle. Okay? So, this is what is necessary to solve the problem, and this is what the basis for going forward into the emergent gravity paradigm, which I am going to talk for the remaining part of the lectures. Okay? Fine. So, I have to switch the file. These files are sort of based on topics, while okay, this is the correct file. Okay. So, this is the last part of the talk, and this part is going to be different from all the previous in the sense that this is going to be more like a colloquium style. So, I am not going to derive for you all the results. I mean, even in the previous one I did not do too much, but level of mathematical details I am going to keep lower, because you can go and read it up in standard references. Most of the references I will be citing, or you can send me an email if you want a particular result. So, results you have to just take as assumption like in a colloquium. But I am going to spend a lot of time talking about the concepts, because most of the mathematical results which is coming in, I have given talks at various places, some of you might have listened here or whatever. But I am going to concentrate on the concepts and the big picture, because the entire group of talks was to start with 3 clues to quantum gravity, where in 3 places where there was contact and conflict, and I want to use all these 3 clues to come up with a model for quantum gravity, or an approach towards quantum gravity, which I call the emergent gravity paradigm, which is a program which many of us have been involved in here. And it has gone up to some stage, and there are lots of open issues. So, I will talk about the broad picture so that you will know which direction to proceed if you want to look at it. I will also tell you what are the concrete result, rigorous result which we have, and what are the sort of tentative places which is under exploration. So, that is going to be the spirit of the last lecture. So, I had already listed these 3. So, just to remind you, the contact and conflict, the quantum connection between G and H cross comes in 3 levels. So, first is that there is a Planck area which is G H cross upon C cubed, which seems to play an important role. We already hinted at this role when we discussed the black holes. I told you that the gravitating energy of the black hole is half n kT, where the n is the number of degrees of freedom, and the number of degrees of freedom was the area of the event horizon divided by the quantum of area. Okay. So, the area divided by quantum of area acting like a degrees of freedom is a theme which will keep coming up, but it is going to play a lot more important role later on. Then we have the issue of cosmological constant, and I had already told you that the fact that this has this tiny value tells you 2 things. First, if any principle is going to describe its value, that principle has to be protected by having a theory in which TAB going to a constant plus delta AB is an invariance, because otherwise there is no way you can get this number. Then additionally you need a principle which will give you this. So, there are 2 ingredients, and I will show you where both these ingredients come. The first ingredient is clean and fairly rigorous, while the second ingredient is going to be somewhat speculative, which will come very much towards the end of the talk. And third, and in fact what we will take these two first, and this is going to come up right at the end as a added extra in some sense, even though it will make its presence felt all throughout in terms of this equipartition theorem that energy is half n kT. The third is something which we spend a lot of time on, that which you had to go back to what I said in the last part of yesterday's lecture. Take an arbitrary space-time, go to an arbitrary event, construct a local inertial frame. Then you boost it to a local Rindler frame. Then there is a horizon, and the vacuum fluctuations in the local inertial frame will appear to be thermal fluctuations in the local Rindler frame. So, because of which at any event in space-time, like here, there are observers who will attribute a temperature to that, and they have an event horizon which is killing the information or blocking the information. So, locally in that neighborhood there is an entropy density, lack of information is entropy, and entropy density and a temperature. So, there is a heat density. So, null surfaces are endowed with some heat density, and this is a concept which comes from this thermality of the horizon. So, these are the three ingredients which we want to put together and come up with a theory. So, I will describe what all we can do in that emergent gravity paradigm, and then in the end I will summarize how this comes about. So, let me see, so this I have already said. These are the three clues which allow us to understand the microstructure of space-time. Okay, this part is starting from the cosmological constant again, so that I will do in tomorrow's lecture. So, we have